and the pump curve make up the performance curve. Now within this section we might get a little bit technical, but bear with me. So the system curve looks a little something like this, with flow rate across the x-axis and pressure in the form of meters, elevation or head on the y-axis. Now what this shows is static head, which is the elevation height between the liquid levels, pipework friction loss, which increases as the flow rate increases, and the atmospheric pressure. However, in many cases where both ends are open to atmosphere, we can typically ignore this. It all starts with the Bernoulli Equation, which can be considered as the conservation of energy principle appropriate for flowing fluids. Basically, within a fluid pipe, a point of higher fluid speed will have less pressure than a point of slower fluid speed. So the Bernoulli's equation looks a little something like this. So knowing that the properties at all points of the system are equal, we basically have the equation where parameters at point 1 is the same as all the parameters at point 2. Now we can rearrange this equation by dividing the density and gravity, which now makes it look a little something like this. And why is this important? Well, it's because it spells out the three main parameters of the system curve: kinetic head, pressure head and elevation. However, the problem with Bernoulli's equation is that it does not consider energy loss. And since there is energy loss, one parameter that needs to be considered is friction loss.